Hi, Rajan this side. Welcome to my YouTube channel. So today we will discuss the problem asked in today's Codeforces Round 1050. So let's start with the first problem. It says Farmer John has an integer x. He creates a sequence of length n by placing alternate integers x and minus x, and that start with x, right? So for example, for n is equal to 5, the sequence would be x minus x, x minus x, and x, right? And he asked you to find out the sum of all the integer of the sequence. So we know that the numbers are placed in alternate plus minus, right? And they are the same number. Same x is placed but with alternate positive and negative. And we know that the sum of two consecutive number will always be 0. See, right? Because the two consecutive number will always be plus x or minus x. So the sum would be 0. So it simply means that for n is equal to even, so for n is equal to even, your half of the number would be x and half of the number would be minus x. So total sum would be 0, right? So for when n is even, your total sum is going to be 0. For n odd, your sum would be x, because, so let's take this example. For n is equal to odd, we have 5 numbers, right? X minus x, x minus n, and x. We can make a pair of these two numbers. So what you will left with just x. So for n is equal to even, your sum is going to be x, otherwise your sum is going to be 0. Here is the code of first problem. So for each test case, you take an input x comma n and just check if n is odd, just output your given integer x, otherwise your sum is going to be 0, so output 0, right? So yeah, let's look at the second problem now. Second problem, you are given a 2D coordinate plane that ranges from 0, 0 to x, y. So your initial location is 0, 0, and you want to reach at x, y, right? And there are few horizontal lasers and there are m vertical lasers, right? So and their laser range starts from 0, a to x, a for horizontal, and for vertical lasers it ranges from bi, 0 to bi, y, right, in a straight line. So you may move in any direction to reach at x, y, but your movement must be contiguous, right? Continuous curve. So every time you crosses a vertical or horizontal laser, it counts as one crossing. Particularly if you pass through an intersection point, right? It counts as the two crossing. For example, let's say you crosses at this point, so it will be counted as two crossing, right? So you have to find out the minimum number of crossing necessary to reach at x, y, right? So this is also a pretty easy problem. So we know that this is my matrix, so this is x 0, 0, and we have to reach at x, y, right? So let's say there are few lasers, right? Few horizontal lasers. Let's say this is one laser. By the way, your laser would be like below y, so it would be like this. For horizontal laser it may look like this. Vertical laser should be this one, for example, this one, right? So you have to start from here, you have to reach at x, y, right? So we know that we have to like to reach at x, y, you means you have to, so let's take the horizontal distance. You have to make a distance of, you have to cover a distance of y in any case, in whatever, like, so to reach at x, y, you have to cover at least this much distance in a horizontal direction. Similarly, you have to cover at least sorry, this is x, at least y distance in a vertical direction, like you have to, no other option. Then why should I travel in this path? There is no benefit of doing it, because it might possible that you cross at this intersection, right? And this intersection will be counted as two crossing. So it's better to follow this path, go in horizontally and then go vertically. Go horizontal, I mean go through axis, go through horizontal axis and then vertical, then vertically, right? So then the total number of crossing would be, the minimum would be how many number of vertical lasers you have. Let's say there are n number of horizontal lasers, and m number of vertical lasers, right? So the total number of crossing would be, the minimum crossing would be n plus m. You cannot avoid it. You have to cross at least n plus m number of lasers, right? So yeah, this is all about the first problem. Let's see the code now. This is the code of second problem. So for each test case, we have taken the input of n, m, x and y, right? And like as we have seen the explanation part, the position of these lasers doesn't matter because we anyway have to deal with these lasers. We cannot avoid these lasers in the path. There is no way like we can avoid lasers to reach from 0, 0 to x, y. We have to deal with them, right? So the better way is to don't follow the like don't have a path that goes at the cross point, the intersection point, right? So because intersection point would be counted as two crossings, so just avoid that. So your total number of crossing would be, the minimum crossing would be n plus m, right? So yeah, just output n plus m. These positions of lasers doesn't matter, right? So yeah, this is the code of second problem. Third problem says farmer John is running a fitness gram pacer test. So he takes 1 minute to reach the other side of the gym. So at start of each minute, he can either choose either to run or just stay in that place, right? So if he chooses to run to the other side of the gym, he gains 1 point, right? And FJ will run the pacer test until the start of mth minute, all right? So initially at the start of the 0th minute, FJ is at the starting side of the gym, which we will denote as side 0. So we have two sides, side 0 and side 1, right? And he will be starting at from side 0. So the pacer test audio plays n number of times. At the start of AIth minute, FJ must be at the BIth side, right? So BIth could be either 0 and 1. So at the start of AIth minute, it must be present at the BIth side of the gym. So we have to find out the maximum number of points FJ can acquire while ensuring that he meets all the audio requirements, right? So yeah, this is a pretty interesting problem. Let's see how we can approach it. In the third problem, it says we have a gym that has two sides, right? Side 0 and side 1, and a person if runs through this side, he will gain 1 point, right? Plus 1 point. So let's say at any particular time t, you are at side, so it could be either 0 and 1, let's say, right? And let's say the next audio, so we have a list of audios, right? We have to follow those audios. So let's say at the ith audios, it says at the start of 8th minute, you should be at the bth side, right? So this is, let's say this is my current side. So there are two cases. First case, if this expected side, like the next side, is equals to my current side. So let's say this is my current side. Or the second case could be if this b is not equals to my current side, right? B is not equals to current side. So let's test the first test case. If my b is same as the current side, so the expected size and your current side is same. In that case, let's say there is a difference. Difference is equal to a minus t, right? The next minus previous time, next minus t, a minus t, right? Can I say if I'm at the same side, let's say if this diff is greater than 2, greater than or equals to 2, it means that I can go and come here, right? I can go and come here. So because I want to gain the maximum number of points, right? So if it is more than 2, I can go and come here. So the side, because we want my next side would be same as b, right? So here in this case, your total answer plus equals to, I mean the total points would be incremented by, let's say this is my diff divided by 2 into 2. I mean, because I want the even number, because to go and come here again, you need two runs, right? One to go and one to come. So this simply means that let's say your diff is even. If diff is even, your plus equals to diff exactly same. But if diff is odd, I want to your total point should be diff minus 1, increment by diff minus 1. So that's exactly what this is doing, right? Now if the b is not equals to side, if my current size is not the expected side, in that situation first you have to move to the opposite side, right? So in this situation your points plus equals to 1 plus, because we have to move to the other side, right? Now what you left, how many like what is the difference in time left? The time left is a minus t minus 1, because we have taken one extra move to reach to the other side, right? So once you do 1 plus means you have done one extra the initial move. Now your side become the b, now your current side become b, right? So in that situation, and you left with a minus t minus 1. So again this is same diff divided by 2 into 2, but here in this case diff is a minus t minus 1, and here diff is a minus t, right? So yeah, this is the explanation part. Let's see the code of third problem. So here is the code. For each test case I taken n and m, right? So answer equal for initial your answer is 0. Now we know that we have to start from 5 0 and your initial time is t, and that is also 0, right? And for each test case I took the input of a comma b. So a is my current time and b is my current side. The difference is a minus t, the previous time, right? So this is my difference. Now there are two test cases. If like two cases, if my current side is same as b, in that situation your answer would be plus equals to diff divided by 2 into 2. I explained what this means. Now if that's not the case, if your current side is not equals to b, you take one extra move to reach to the other side, then plus now since you already taken one extra move, now what you left, how many number of how many minutes you left? The minute left is diff minus 1, and then apply the same process, that divided by 2 into 2, right? Now and once you do that, so this is your total point. Now your just update your time inside, so now your current time become a and your current side become b, right? So just a corner case you have to handle. So let's say this is my last audio to take care of, right? And so let's say this is my last audio. We know that so this is my current time, but we know that the total movement lasts for m minute, right? So after that you can freely since you have satisfied all the inputs, right? We have to satisfy all the audios. So we have already satisfied all the audios, so now you can freely move. So how many minutes you have? You have m minus t number of minutes. So just increment your answer. Your total points would be incremented by m minus t, right? And at the end return an answer. So yeah, this is the code of third problem. Now let's look at the fourth problem. In the fourth problem, it says farmer John has a switch. That switch is initially turned off, and he also has n number of fields. And the ith field has ai number of let's say I would call it mangoes. Ith like ai number of mangoes, ith field. Now he will visit all the fields in any order he wants, right? And but each field should be visited exactly once, right? And the farmer seems to have minds of its own, right? So he can choose any order, and right before visiting the field he will check if the field has either even number of mangoes or odd number of mangoes. So if the number of mangoes are odd in the field, he will first toggle its states. Toggling means if the switch is initially turned off, it will be turned on, and if it was initially turned on, it will be turned off, right? And then if the switch is on, he will cut all the mangoes in that field, and he will take it all the mangoes, right? Otherwise if the switch is off, he will simply visit the field but he won't be taking any mangoes. And so he want to visit all the ant field in optimal order, such that the total number of mangoes taken is maximum, right? So yeah, this is an interesting problem. Let's see how we can approach it. We know that there are n number of fields, right? And each fields may contain either even number of mangoes or odd number of mangoes, right? So we will divide into two parts. One list would contain all the even mangoes field, right? So let's say this is even and this is odd fields, right? So all these would be odd number of mangoes in the field. Let's say this is 1, 7, 3, 9, 5 and 11, right? And one list would be to contain all the even number of mangoes. So 2, 8, 10, 12, 4, 6, right? Now let's take a case when you have all odd. So we know that there is a switch, right? There is a switch which initially is off, right? Initially is off. And so there are two states, either it could be off or on. But we know that if you want to take the mangoes from the field, your current state should be on. Only then you can take the mangoes, right? And we know that initially it is off. So to make it from off to on, we know that we have to and one more thing, if you remember in the problem statement, it can be toggle. So it will be toggle when you like when you want to visit a odd number of mango, like when you want to visit a field that has odd number of mangoes. In that situation your switch would be toggled, right? So we know that initially it is off, and to take it, it should be on. We know that we have to make it on, like, so we have to make the toggles like we have to toggle it. It means that we have to visit at least, like we have to visit one odd for sure to make it on, right? So let's take a case when like there is no odd number of mangoes in the field. In that situation you cannot take any of the mangoes because you won't be able to toggle the switch. You won't be able to make the switch on, right, if you don't have any odd number of mangoes. So in that situation your answer would be 0 if you don't have any odd number of mangoes. If you have, now we know that we can make the switch on, right? So, and we know that we have to take one of the odd mangoes, right? Then I think the most optimal way would be, so optimal means you have to find out the maximum number of mangoes you can take. Just take the maximum, just take out the maximum mangoes in any of the field. So what we will do, we will create a two list. One would contain even, one would contain odd number of mangoes. We would sort them in ascending order, right? Now we will first take the maximum odd mangoes. Sure, your answer initially your answer would be the odd dot back, right? Odd dot back. So this is the maximum mangoes initially you would take. Now your switch become on, right? Now we know that if you visit a even mangoes, the toggle won't be changed. It would be in a same state. Then what we will do, we will to get the maximum number of mangoes, we will first take the maximum odd mangoes. Then we will visit all the even mangoes, because we know that your state is not going to change, means your switch is going to be on once you visit the even mangoes. So just visit all. Now it means that your answer is equal to odd dot back plus all the even mangoes, all the even mangoes, right? Now we visited all the even mangoes, your switch is still on. Now what you left with these many odd number of mangoes, right? But we know that once you visit odd mangoes, your state will be toggled. So it will be off if it was on before, and it will be on if it was off before. Means that, and we know that my current state is on. It says that you cannot take all the odd mangoes because your state is going to be toggled. Now we know that if you want to visit a odd mango, your state would be toggled first, right? And we know that after taking all the even number of mangoes, your state is still on, right? And what you left with these many odd mangoes, right? So if you want to visit odd mangoes, your state would first change to off, right? And then you go and visit that odd mangoes, right? Since the state is off, so let's say these are the remaining odd mangoes. So let's say like you want to visit odd mangoes, your first state would be toggle. So now it become off. Once it become off, it means that you cannot take that any of the mangoes. If you cannot take any of the mangoes, then it's better to use use the minimum mangoes to toggle it. So what it's doing, it just uh, doing a toggle, because you cannot take any of the mangoes if your state is off. So use minimum one to toggle and use maximum to take out the mangoes. So let's say I want to visit the minimum one, so my state is off now, you cannot visit, right? But now for the second one, let's say you want to visit the next odd mangoes. So again your state would now be toggled, so it would be on now. If it is on, it means that you can take the mangoes from that field, right? It's better to take the maximum one. I will take the maximum one. So let's say these are in a sorted form. It is 1, 3, 5, 7 and 9, right? So I will visit this to toggle, to first toggle from on to off. Now now for the second one it will be on now, right? So I will take it out. Now for the rest, again, I mean all these are odd, right? So again your state would be toggle to off. It means that you cannot take that. So if you cannot take it, so then so then the optimal way is to visit the minimum one. So minimum is 3, like the 3 mangoes left. So go there, but you cannot take it because your state is off. Now you come to 7, use 7. So once you visit 7, your toggle would become on. Since it is become on, you can take it, so just take it out. So take this one. Now what you left with 1, so you can only change the toggle, you cannot take it because your state is off, your switch is off, right? So it means that you can only take half of the remaining odd mangoes, you cannot take all, right? So, and those halves, like the optimal would be to take the maximum half, right? So for example here 1, 3, 5, 7, 9, you take the half is 5 divided by 2, right, which is 2. So just take the max 2 odd mangoes, right? So it will be total. So your answer is first add odd dot back the maximum one plus remaining even plus half of the remaining odd. So your total odd divided by 2, the maximum half of the odd mangoes. Yeah, this is the explanation part. Let's see how we can write code for it. This is the code of fourth problem. So for each test case, I initially took the number n. Now for all these numbers n, like the taken input of all these n numbers, if the number is odd, I have kept those numbers into the odd list, and if the number is even, I have kept those numbers into the even list. Now once you push the numbers into the even and odd based on the number, now what I have checked if there is no odd mangoes present. The reason is, if there is no odd mangoes present, you cannot toggle the state, right? Because initially your state was off, and to take the mangoes your state should be even, but the state would be toggled only if you have a odd mangoes, right? So if there is no odd number, you cannot change the toggle. So it means that your answer would be 0. You cannot take any of the mangoes. Otherwise you can take the mangoes, right? So initially first sort both these even and odd list. Now since you can take the mangoes, first take the maximum odd mangoes. So you take it, and once you take it, your state would be changed from off to on, right? Now your switch is on. So once your switch is on, you take all the even mangoes. So first you have taken the maximum odd, you have removed it from the list, then you have taken all the even mangoes. Now we know that we cannot take all the remaining odd mangoes, because because there is a toggle, the switch would be on and off, uh, like alternatively, right? So we can only take half of the odd mangoes. So please check out the explanation part I have explained there. So here your total odd mangoes are odd dot size, so divided by 2. These are the mangoes which you can take. Now since you only take half of the mangoes, then it's optimal, like the optimal way is to take the maximum half of the odd mangoes, right? Since we have sorted in ascending order, right, so minimum to maximum, so take it from the back. So I have taken all these half mangoes from the back, and at the end return your answer. So yeah, this is the code of 4 problem. Now let's look at the fifth problem asked in today's contest. In the fifth problem, it says farmer John has an array A that contains n positive integers and integer k. Now let there is a subarray from index L to R in the given array A. He performs the following procedure to independently determine if the if this subarray from index L to R is awesome. Now there are few conditions. So initially your it has k number of empty multiset. So these multiset are numbered from 1 to k. Now for all these elements in the given array A, if the numbers belongs to the subarray, I mean subarray means your index is from L to R, you can only keep those numbers into the multiset 1, right, the first multiset. Otherwise you can keep the number into any of the multiset. It could be either 1 from k, like there is no restriction, right? Now the subarray A to R is called awesome if there is some way to place elements such that for every element v, all the multiset contains the same number of elements value v. All right. And in other words, he wants to make all the multiset contains exactly same element. Like, so after keeping the number into the multiset, at the end all the multisets should be exactly the same, right? So the ordering doesn't matter. So like ignore the ordering, but the numbers, like all the multisets should contain exactly same sort of numbers, and we have to output the how many number of awesome subarrays which we can get, right? So yeah, this is really a good problem. Let's see how we can approach it. In the fifth problem, we are given an array, right? So each array may contains duplicate numbers, right? So what we will do, we will first, for each number we will count its frequency, right? So let's say the number is num, right? Its frequency is f, right? We know that we have to keep these numbers num, which is present f number of times, f its frequency, into k multiset, right? We have k number of multiset, right? 1 2 3 up till k, right? So k number of multiset, and all these multiset would be identical, should be identical at the end. Means all these numbers should contains the same number of same number and with the same frequency, right? It says that so first your app should be multiple of k, right? For first check if any of the like the frequency of each unique number, if any of the number is like if that is not divisible by k, your total number of awesome subarrays would be 0, because we cannot make all the k multisets identical at the end, right? So just check if any of the frequency is not multiple of k, your total number of awesome subarrays is 0. Otherwise, if all the frequencies are multiple of k, right, if all the frequency are multiple of k, so let's say so it means that each of these multiset should contain f divided by k number of times this number. So this is my count. These many number of times your nums should be present in each of the multiset, right? It means that in the given array, let's say that you have taken a subarray from L to R, right? We know that we can keep f divided by k number of times this num, right? It means that your subarray, let's say I'm saying this is my awesome subarray. It means that the count of m, like the count of this number in this range in this subarray, must be less than or equals to f divided by k for sure. It cannot be more than f divided by k, because we know that for all the number in the given subarray L2R, it will be going to this first multiset, like none of the other multiset like in which we can keep these numbers. If the number, let's say the reverse case, if the frequency of num in this subarray is greater than f divided by k, f divided by k, it means that we have to keep all these numbers, all these like all the numbers f divided by k, like which is more than f divided by k number of times, into the first multiset. And that doesn't satisfy our requirement, because we know that to make all the multiset identical, each of these multisets should have f divided by k number of times. But if it is more than f divided by k, your first multiset would contain more than f divided by k, which shouldn't be. That is why in any of the awesome subarray, this num should be the count of the frequency of num should be always less than or equals to f divided by k. Why not exactly f divided by k? Let's say this is less than f divided by k, right? So what we will do, we know that if it is less than f divided by k, we will keep all the, these number of times into the first. But we also know that for others, like which is beyond this range L2R, we can keep in any of the remaining multisets, right? Not remaining, like including one also. So whatever is left, right? Whatever is left, let's say this number is x, right? So how many number of nums left? F divided by k minus x, right? What we will do, we will keep these many number of times again into a, because we know that there is no restriction on those numbers which is beyond this range. We can keep into any of the multiset. So right, I hope you understand why the frequency of num should be less than f divided by k in this range, right? So if you understand this part, I think you have almost solved the problem. Now the last thing which we will do, so let's say this is my array, right? So let's say this is my current index I. Now what we will do, we will try to find the list index till which you can make the awesome subarray. So from index I, let's say this is my one subarray, this is another subarray, this is another subarray, this is another subarray, right? So I want to find what is the minimum index, the list index j till which you can make the subarray awesome, this subarray awesome, right? Because beyond this point, right, because we know that once you keep on going left, your frequency is keep on increasing, right? So we have to restrict the frequency. We know that the awesome subarray must contains at max f divided by k number of times this num. And by the way, this num is applicable for all the unique numbers, right? So there must be some point where beyond that you cannot make the subarray awesome. So for each index I, we will try to find the list index till when you can make the subarray awesome, right? So to do that, what we will do, we will so for each of the number, right, for each of the numbers, we know that the number of, like the frequency of number is f. We will also store those f number of times, like we will store the index of this num, right? So let's say these are the indexes. I'll store it in like in a vector. Let's say this is my current index. Let's say this is the index store here is something, let's say p, right? So I'll create an array called list index, right? List index of all the n numbers. We know that like the definition of list index we also already know. For each index you will try to find the list index till when you can create the subarray awesome, such that your right index is present at ith index. So this is, let's say, my p, and we know that for this num we can at most keep like we should be putting f divided by k number of times in the multiset, right? So we will go till the here, such that these count is f divided by k. We know that for this index p, we cannot create a awesome subarray with this, which is just like, which is uh, beyond f divided by k number of times, right? Let's say this is p and this index is something called, let's say, q. So if this index like if this length is more than f divided by k, we cannot make an awesome subarray having these two index as a l and r, right? So it means that we will update the list index of p is equal to maximum of list index of p, comma, these numbers, index of let's say this is my idx array, idx of, let's say this is my current index I minus f divided by f divided by k, right? So this is my, so the list index would go this plus 1, because we cannot form the awesome subarray having this as a left index, so it should be just plus extra, right? So this is my list index updation, right? And so this is how we do it. But one more thing to keep in mind, this is not sufficient. We have to consider the last case. For any number, for any index I, so it means, so once you calculate this part, we know that my list index I is calculated, right? But to note in mind, your list index of I should be maximum of list index of I, comma, list index of I minus 1. Just think about, just pause the video and think about it, why this last case is required, right? Once you calculate this part, why this is not sufficient? Because we know that for any index I, we know its last list index. Let's say, it means that, what it means, let's say this is my last list index, it means that I mean, like, I can form a awesome subarray for this number such that these are the awesome subarray, right? But let's say the previous number has the list index only till here, right? Only till here. And we know that an awesome subarray must contain all the numbers of having frequency less than at most f divided by k. That is why I have to consider the previous numbers also. That is why I have updated my list index of I. Also, I've considered the previous number, list index of I minus 1. So yeah, like if you try to dry run, or if you try to like note down in the, just do a rough understanding in the pen and paper, you would understand it completely, right? So yeah, this is the explanation part. Let's let's look at the code now. This is the code of fifth problem. So for each test case, I have taken n and k. This is my n and k, right? And now I have taken an unordered map that will kind of store the indexes for each of the unique numbers. So I have taken the input of all these n numbers. I have pushed the index for that particular number into this unordered map. Now this is my list index. So initially the list index for all the numbers I have taken at 0, right? It means that I can, I have assumed that initially I can form the awesome subarray for each of the index as a right index. I can form it for all the left index. So the list index would be 0, right? Now I'm going through each of the unique numbers from the map. This is my frequency. I first check if any of the frequency is not a multiple of k. If that is true, if there is a number which is not multiple of k, return like C out 0. There is no awesome subarray possible. Otherwise, this is my count, right? This is f divided by k, which is the count. So this count number of times this number would be present in each of the multiset, right? Now what I'm doing here, I'm updating the list index, right? So I started from count. I'm going through all the numbers, the frequency I plus plus. Now the list index of that number should be maximum of that number, comma, index of I minus count plus 1. So whichever the number present at just like beyond this count, that is the minimum number plus 1, because we cannot form the awesome subarray for that number, so just take 1 extra, right? And after that, just consider the last test case, like the last corner case which I have explained. Like we also have to consider the previous numbers, right? So your list index of I should be maximum of this comma previous list index, right? And yeah, that's all. Now this is my answer. Now for each of the numbers, what is my maximum length? The maximum length is I minus list index plus 1, right? So like for L2R, the total numbers are R minus L plus 1, right? So this is what exactly R minus L plus 1. So these many number of subarray you can form, right? From let's say this is L, this is R, so you can form R to R, R to R minus 1, R to R minus 2, till R to L. So the total is these many number of times subarray you can get. So your answer would be answer is incremented by this length, and at the end return the answer. So yeah, this is the code of fifth problem. If you find the video helpful, please like, share and subscribe to my channel. Thanks for watching.